So today we're continuing on from yesterday's lecture. Let's see, what did we talk about yesterday? Yesterday we talked about how to prove Gauss's law with a sphere, and then we used Gauss's law to determine the electric field from some basic shapes, like the electric field from a line of charge, and then the electric field from an infinite surface, right? Mm-hmm. Well, now we are going to repose a question that we've all seen before. The question goes like this. Let's pretend that you have a plastic sphere. And this plastic sphere has charges, like positive charges, inside its material itself. That can't move, right? Because it's plastic. The charges can't move. If it were a metal sphere, what would happen to the charges? They would all go to the surface because they hate each other, right? But in a plastic sphere, the charges are stuck inside the bulk of the material itself. And what that means is you've got charges just uniformly distributed throughout. And what I want to know is if you were exactly at the center of that plastic sphere, what would the field be? Why would it be zero? Yeah, anything on the right would balance anything on the left.
Because the distance is
Yeah, well, anything on the right side would balance anything on the left, so there would be no net field to the right or left. And anything above would balance stuff below, so there'd be no net field up or down. So the net field would be zero at the center. And then at the edge, of course, we know KQ over R squared, right? So I want to know if you were to make a plot of electric field versus distance, we know that from once you get out to the edge, it's just going to decay away, right? And we know it's the center at zero. What happens in between the center and the edge? What do you think the answer is? Is it zero the whole time? Or does it do something else? What's the answer?
I think it's going to be a straight line.
I think it's going to be a straight line too. Why? What's your logic? What's your reasoning?
Because the relationship, like when I think of the equation, I feel like it's not based on an R squared. It's just based on
Just because you feel like it should be based on, instead of 1 over R squared, it should be based on the electric field should build with R?
Yeah.
Why?
Because...
Shut up.
Have we done this problem before?
Yes.
Raise your hand if we think we've done this problem before. Everybody raise your hand. Yes, we've done this problem before. When?
Gravity.
The gravity, when you're falling through a planet. Well, guess what? It's exactly the same for exactly the same reason. We are redoing that problem, falling through a planet, just now with electric charge rather than gravitational field or mass.
So as you get further from the center, the amount of charge that's affecting you gets bigger.
Exactly. As you get further from the center, the amount of charge that matters gets bigger and bigger and bigger and bigger, and therefore the field gets stronger and stronger and stronger. We are going to redo that problem that we did a couple weeks ago, falling through a planet, just in electric world instead of mass world. Does that make sense? All right, so here we go. Oh, by the way, we are going to use something called Gauss's law to do it. But guess what? We actually used Gauss's law for falling through a planet too. I just didn't say it was Gauss's law.
You're a trickster.
Ha! All right, so here we go. What matters? First, imagine a sphere where all the charges was on the outside, say like a conducting sphere. Pretend that. What would the field be inside a solid conducting sphere where all the charge is on the outside? What would the field be?
Inside?
Inside.
Zero.
Zero, right. Be for that reason we talked about before. Like, yeah, okay. So the stuff that is outside of where you currently are doesn't matter, right? So the only thing that matters is the charge that's inside of your current radius, right?
Correct.
Ha-ha! All right. So, let's move on. Oops. I think I actually drew a picture on the wrong picture. Oh, well. Now, let's figure out the field when there is a uniformly distributed charges inside the sphere itself. What we say is we're going to first pick a radius. Right? Guess what? Our radius of our Gaussian sphere is going to be. What's a good radius?
R.
Little r.
Little r.
Because what's big R?
The total.
What's bigger? Big R.
Big R is bigger, right? Big R is the radius of the entire sphere. So when you're doing these problems, you need to make a distinction between little r and big R. Big R is a constant, little r is going to be a variable. All right. So we need to figure out the charge inside of this little Gaussian surface on the inside. Well, the charge is going to be, would that be the charge density times the volume? It'd be the charge per volume times the volume would give you the charge enclosed, right? All right, so we need to figure out charge density somehow. Charge density would be charge per volume, right? But you could do that for the whole sphere. It'd be charge density would be the total charge of the sphere divided by the total volume of the sphere, right?
Yeah.
And that charge enclosed by this little surface would be the volume of this little surface
Times the charge density.
times the charge density of the whole thing. In other words, the volume of the little sphere divided by the volume of the big sphere times the charge of the big sphere. All right, and you can just do that. The volume of the little sphere is 4/3 pi little r cubed. Volume of total is 4/3 pi big R cubed. The 4/3 and the pi cancel. And you're left with the charge of the little sphere has to therefore be little r over big R to the third power times the total charge of the whole sphere. Does that make sense? All right, so you're going to have to be able to do this, by the way, on a test. All right, next. So we've got the charge of the little sphere. That's good. Let's move on. Gauss's law says that the electric field times the area is equal to the charge enclosed over epsilon naught, right?
Mm-hmm.
Yep.
Okay, so electric field is what we're looking for. Area, what's the area of a sphere? 4 pi r squared. And then the charge enclosed is this equation right here, r over r cubed. You do some math, and what you end up with is...
Bless you.
total charge of the whole thing divided by 4 pi epsilon naught r cubed times r. How many constants do we have? No. Is Q constant?
Yeah.
Yeah. Is 4 constant?
Yeah.
Pi, epsilon naught. Is capital R constant?
Yes.
Yes. Is little r constant? No, that's your variable. So guess what? The electric field is a constant times r. What kind of equation does that make?
It's a line.
That's a line. Got it? It's a line. Therefore, the electric field grows linearly
Yay.
on the inside till you get to the surface. And then it drops away. All right. So it creates a piecewise function from here to here. It's linearly increasing. From here to infinity, it drops off according to 1 over r squared. Does that make sense? All right. That's it. Tomorrow we're going to extrapolate this out and do shells. But for tonight, this will do you.